Good morning. My name is Carlos Jorquera. I'm with Boulder Imaging, and I'm going to be talking a little bit about quality control, inspection, and measuring challenges that can be addressed with machine vision, particularly vision technologies that have become recently available. It's rather interesting that given all the great automation technologies we see here today, that the most common and popular way to inspect product even today is through rather traditional techniques using methodologies and instruments such as micrometers, calipers, comparators, and test rigs of various sorts, all of which are highly manual in nature and obviously involve a high degree of human interaction through some sort of operator. Even with the more automated machines such as CMMs, coordinate measuring machines, the process is very time consuming and again involves human oversight. And therefore, all these methodologies are only applicable to lot sampling. They're not suitable for 100% inspection capabilities. Current technologies allow for a wide range of inspection capabilities. Probably the most common of which is the use of smart cameras. These are essentially imaging sensors that have back-end processing capabilities that are particularly suited for specific applications that are generally highly constrained in nature. For example, things like barcode reading, looking for feature measurements, defect detection on surfaces, things of that nature, presence or absence of components or parts. More flexible technology is general purpose machine vision systems that perform generally the same functionality that smart cameras do, but provide a higher level of flexibility and tunability to the process. But ultimately, they're generally meant for single tasks, meaning that it's a primary one inspection function that they provide. Laser profilers are technologies that make use of scanning lasers to make pretty detailed measurements on surfaces of parts. And these are gotten quite good at making pretty accurate measurements down to 10 microns or less for small parts. And when you incorporate them with a CMM, coordinate measurement machine, accurate to those levels even for fairly large parts. In general, all these technologies, however, are limited in terms of their scope. Smart cameras and machine vision systems are limited to constrained environments where either the illumination has to be highly controlled, the speed of the process is controlled in some form or another, the presentation of the product or part also has to be constrained. So they solve a wide range of problems, but it's very important to keep in mind that those problems have to be constrained in their nature in order for these products to succeed. In terms of the laser profilers, CMM, using optical probing technologies, these are becoming extremely accurate, but their speed is still a limiting factor. The traditional CMM systems, what would take them an hour to measure for a fairly complex part nowadays can take in the order of 10 minutes to do. So there's been vast improvements there, but obviously when you're talking in the order of minutes, it still constrains what you can do with that in terms of real-time inspection. Recent trends in manufacturing have put some very tough requirements on inspection technology. Foremost is the need to inspect 100% of the product. This is becoming much more the norm in industry today, where even one defective part that gets through the process can can lead to catastrophic type of consequences. So to achieve 100% inspection requires speed, foremost, of course. Not only to keep up with the production rates, but to enable the ability to inspect the part for all its possible parameters that can produce a defect. So what this means is that you're not just doing a single inspection on that part, you're doing potentially 100 different inspections simultaneously on that part. 100% inspection, of course, also dictates that you have to be in line with the process. You have to be able to incorporate multiple sensors throughout multiple locations, possibly within the line, and doing it in a very much integrated way so that it doesn't become cumbersome or overly complicated for use in a daily production environment. It's got to be versatile, obviously easy to use, and also important is the ability to provide access to all the data that is being generated. Obviously, you have a huge number of sensors looking at these parts going through the system, and that the data they gather becomes extremely valuable not only for quality control but also for process control, determining what is working in the process and what isn't, and that information gives you the ability to make real-time adjustments to your process. Recent technology that's been developed that can finally fulfill 100% inspection requirements, what we call high-performance multifunction vision systems. This is something that Boulder Imaging specializes in developing, primarily in our vision inspector line of products. The primary enabling capability is the raw speed, the raw processing power behind these systems, which are capable of performing from hundreds to thousands of inspections per second. And again, that speed is not only necessary for the speed of the line, how many parts you're producing per minute, but what it enables you to do is do simultaneous inspections. You can do dimensional analysis on the part together with surface quality, color, composition, all simultaneously through one integrated system. And again, the importance of having a very integrated system becomes critical because real estate, space in the production environment is very critical. It needs to be a system that's fully integrated, composed of a centralized way of capturing all that information and processing it quickly enough. Typically, today, if you use standardized technologies, you may be able to solve your inspection problems, but it may very well end up requiring 20 to 30 machine vision systems or smart cameras to do the tasks that one of these single systems could be able to do. The way that they can do this is by the use of highly advanced sensors that provide very high resolution imagery and multispectral imagery, providing you a level of characterization of that part that enables determination of not only dimensional parameters, but qualitative type of parameters, surface quality, surface finish, color composition, non-uniformity in the material makeup, and so on. This technology, we believe, of course, is future-proof because of its great scalability potential, and not only does it provide the way to give you a pass-fail mechanism for parts, but it stores and maintains a data set that is easily accessible to determine failure mechanisms in the process itself. Again, for process control engineering, and this data sets are accessible in real time. With the ability to provide those kind of speeds in the thousands of inspections per second, enables brand new capability for processes that today may not even be aware that they can use these type of inspection technologies. Obviously, for addressing ultra high speed manufacturing processes, For example, in web product production, like papers manufacturing, where you're dealing with thousands of feet per second, or metals, where you're producing hundreds of parts per second, or even in applications where it's not necessarily high volume of parts, but it's a performance verification of a product that operates at very high speeds, like in this case a jet engine, detecting ice formation mechanisms and measuring the buildup of the ice through through the whole sequence of startup events. I kept this at a very high level, so feel free to ask any questions. We're at booth 4150, and we're more than happy to answer any questions there or while I'm here as well. Thanks.